When Richard Feynman spoke about inertia as a fundamental property of matter, he was pointing to something far deeper than a classroom definition. He wanted listeners to realize that inertia is not a secondary effect, not a byproduct of friction, gravity, or human perception, but one of the basic ways nature behaves. Matter, simply by existing, possesses inertia. This means that the resistance an object shows to any change in its state of motion is not learned, added, or caused by its environment. It is intrinsic. Feynman often emphasized that physics becomes truly interesting when we stop asking how to use formulas and start asking why nature chose these rules at all. At the most basic level, inertia tells us that an object does not require a force to keep moving. This idea alone was revolutionary in human thought. For centuries, people believed that motion was something that needed constant support, that if you stopped pushing, motion would naturally fade away. What actually fades away is not motion itself, but our ideal conditions. Air resistance, surface roughness, internal deformations, and countless microscopic interactions constantly interfere. When these are stripped away conceptually, what remains is inertia in its pure form, motion that simply continues. Feynman liked to highlight that this behavior is not logically necessary. There is no mathematical or philosophical requirement that the universe had to work this way. The laws of nature could have been different. Objects might have naturally slowed down, curved, or jittered unpredictably. Instead, experiments show an astonishing consistency. An object left alone behaves in the simplest way possible. It does nothing new. It keeps doing what it was already doing. This simplicity is not trivial, it is profound. Calling inertia a fundamental property of matter means that it is inseparable from what matter is. You cannot have matter without inertia. Every atom, every particle, every macroscopic object exhibits it. Even when matter is broken down to its smallest known components, inertia does not disappear. Electrons resist acceleration. Protons resist acceleration. Whole galaxies resist changes in their motion. This universality strongly suggests that inertia is woven into the structure of reality itself. Feynman often encouraged people to be suspicious of explanations that merely rename things. Saying, "Objects keep moving because of inertia," is not an explanation in the everyday sense. It does not tell us why inertia exists. It simply labels the observed behavior. But in physics, naming such a universal behavior is powerful. It allows us to recognize patterns, build theories, and test predictions. Inertia becomes a foundational axiom, a starting point rather than a conclusion. When we push an object and it accelerates, what we are really witnessing is a struggle against inertia. The object does not want to change its motion, not because it has intention or awareness, but because matter responds to forces in a specific, consistent way. The larger the mass, the greater this resistance. Feynman stressed that this is not just a qualitative idea, it is quantitative and precise. The relationship between force, mass, and acceleration allows engineers to design machines, physicists to predict trajectories, and scientists to explore the universe. One of the striking aspects of inertia is how invisible it becomes in daily life. Because we live in a world full of friction and resistance, we rarely see pure inertial motion. Everything seems to slow down eventually. Balls stop rolling, cars coast to a halt, thrown objects fall to the ground. Feynman reminded his audience that this constant interference masks the true nature of motion. The fact that motion appears to require effort is an illusion created by our environment, not a fundamental truth about matter. To appreciate inertia as fundamental, Feynman often asked people to imagine space far from stars, planets, and dust. In such an environment, if an object were set in motion, it would travel forever in a straight line at constant speed. There would be no reason for it to stop, turn, or change. This thought experiment reveals inertia stripped of distractions. Motion without interference is the natural state, not rest. Rest and motion are simply two cases of the same inertial behavior. This idea also changes how we think about forces. Forces are not needed to maintain motion, they are only needed to change it. This shift in perspective is subtle but transformative. It means that the natural behavior of matter is stability in motion, not decay. Nature is conservative with change. It does not alter motion without a cause. Inertia enforces this rule everywhere. Feynman was fascinated by how inertia connects to deeper questions. Why does matter have mass at all? Why does mass measure inertia so perfectly? These questions lead beyond classical mechanics into modern physics. Even when dealing with relativity and quantum theory, inertia does not vanish. It becomes more complex, more nuanced, but it remains central. Objects still resist changes in motion, even when motion itself is redefined in terms of space-time. The fundamental nature of inertia also explains why it serves as a cornerstone for all of mechanics. Without inertia, prediction would be impossible. You could not calculate where a projectile would land or how a satellite would orbit. Every equation of motion assumes that objects behave inertially when left alone. This assumption is so deeply embedded that it often goes unnoticed, yet removing it would cause the entire structure to collapse. Feynman also liked to point out that inertia is democratic. It does not care about composition, shape, or color. A block of wood and a block of steel behave the same way if their mass is the same and external influences are removed. This indifference reveals something important. Inertia is not about surface properties or internal complexity. It is about the sheer existence of matter in the universe. At a philosophical level, inertia forces us to confront the idea that nature prefers simplicity. The simplest possible behavior for an object is to keep doing what it is already doing. Inertia embodies this principle. It is nature's way of saying that change requires justification. Without a reason, nothing happens. This idea resonates far beyond physics, touching on how scientists think about causality itself. When Feynman explained inertia, he was not just teaching a law of motion. He was teaching a way of thinking. He wanted people to see that even the most familiar experiences hide deep truths. Every time you feel pushed back in a seat, every time an object resists being moved, you are encountering one of the universe's most fundamental rules in action. Inertia, as a fundamental property of matter, reminds us that the universe is not chaotic at its core. It is orderly, predictable, and astonishingly consistent. Matter behaves the same way today as it did billions of years ago, and as it will billions of years from now. This stability is what allows science to exist at all. Feynman's genius lay in making people feel the strangeness of this familiarity. We accept inertia because it works, because it matches our experience, but we rarely stop to ask why it should be so universal. By framing inertia as a deep property of matter rather than a simple rule, he opened the door to wonder. He showed that behind every push, every motion, and every resistance lies a quiet but powerful truth about how reality is constructed. In the end, understanding inertia as fundamental means recognizing that matter does not need encouragement to persist. It needs a reason to change. This single insight reshapes how we see motion, force, and the universe itself. When continuing deeper into the idea of inertia as a fundamental property of matter, Richard Feynman would often guide the listener away from intuition and toward disciplined observation. He stressed that the greatest obstacle to understanding inertia is not mathematical difficulty, but the misleading habits of everyday experience. Humans evolved in an environment where friction, gravity, and resistance dominate everything we see. Because of this, our brains quietly assume that effort is required to keep things moving. Feynman's brilliance was in showing that this assumption is not just slightly wrong, but fundamentally inverted. Inertia tells us that motion itself is not fragile. It does not need protection or maintenance. What is fragile is change. Nature resists change, not persistence. This realization overturns a deeply rooted mental model. Instead of asking why an object keeps moving, the correct question becomes, why would it ever stop? The answer, every time, involves an interaction with something else. Inertia guarantees that without interaction, nothing new happens. Feynman emphasized that inertia is not something we can peel away or reduce to simpler ingredients. It is not caused by friction in reverse, nor is it explained by atoms wanting to behave in a certain way. Even when we analyze matter down to its smallest known components, inertia remains. Particles do not suddenly become free of resistance to acceleration just because they are tiny. In fact, their inertia is measured with extraordinary precision in high-energy experiments. This persistence across scales strongly suggests that inertia is not emergent in the ordinary sense. It is foundational. One of the most unsettling aspects of inertia, as Feynman liked to point out, is that physics does not truly explain why it exists. We can describe how it behaves with astonishing accuracy. We can calculate trajectories, predict collisions, and send spacecraft across the solar system using inertial principles. But when asked why matter resists acceleration at all, physics becomes quiet. The laws state that it does. They do not justify it. This silence is not a weakness of science, but an honest boundary. Feynman often warned against being dissatisfied with this kind of answer. In physics, identifying a universal rule is already a profound achievement. Inertia is one of those rules that appears everywhere, without exception. Every experiment ever performed that isolates a system from external forces confirms inertial behavior. The universe has been given countless opportunities to violate this rule, and it never has. That level of reliability is rare and remarkable. Another way Feynman deepened understanding was by separating inertia from human-centered ideas like effort or fatigue. Objects do not get tired. They do not lose motion because they have been moving too long. Motion has no memory of duration, only of state. Whether an object has been moving for a fraction of a second or for millions of years makes no difference to inertia. This timelessness is a crucial clue. It shows that inertia is not a process unfolding over time, but a condition that exists at every instant. This insight becomes especially powerful when applied to astronomy. Planets orbit stars not because something is constantly pulling them forward along their path, but because their inertia carries them onward while gravity bends that path. Remove inertia, and orbits collapse instantly. The elegance of celestial motion exists only because inertia provides continuity. Feynman delighted in pointing out that the same rule governing a sliding puck on ice governs the dance of galaxies. Inertia also forces us to rethink the idea of rest. In everyday language, rest feels special. We think of it as the natural state. But physics makes no such distinction. Rest is just motion with zero speed relative to a chosen reference frame. Inertia treats rest and motion equally. An object at rest resists being set into motion just as strongly as a moving object resists being stopped or redirected. This symmetry reveals that inertia is indifferent to human preferences. Nature does not privilege stillness. Feynman used this indifference to highlight the role of reference frames. Inertia behaves consistently in all inertial frames, meaning frames that are not accelerating. This fact is so subtle that most people never notice it, yet it underpins much of modern physics. The laws of motion look the same whether you are standing still, moving at constant speed, or drifting through space. Inertia ensures this consistency. Without it, the universe would have preferred viewpoints, and physics would fracture into contradictions. As one pushes further, inertia begins to blur into deeper concepts like energy and momentum. Momentum, in particular, is inertia in motion. It measures how much motion an object carries and how difficult it is to alter that motion. Feynman loved how momentum conservation arises naturally from inertial behavior. If nothing interferes, motion continues, and momentum remains constant. Conservation laws are not arbitrary bookkeeping tools, they are reflections of inertia operating universally. Feynman also connected inertia to humility in science. Because inertia is fundamental, it reminds physicists that not everything can be reduced to mechanical pictures or visual metaphors. We can imagine atoms as balls or waves, but inertia does not care about our imagery. It simply manifests in measurements. Push harder, get more acceleration. Push the same amount on something heavier, get less. The rule holds regardless of how uncomfortable it makes our intuition. At the edge of classical physics, inertia begins to intertwine with spacetime itself. In relativity, inertia is no longer just resistance to acceleration in space, but resistance to changes in motion through spacetime. Yet even there, the core idea survives intact. Objects follow paths that require no force to maintain. Forces exist only when paths are bent. Feynman admired how this deeper formulation preserved the spirit of inertia while expanding its meaning. What makes inertia especially powerful is that it does not announce itself loudly. There is no dramatic signal when inertia is present. It is always there, quietly enforcing consistency. Only when we try to change something do we notice it. This subtlety makes inertia easy to overlook, yet indispensable. It is like a rulebook that is invisible until someone tries to break it. Feynman often encouraged listeners to notice how much trust we place in inertia without realizing it. Every time we predict that something will still be where we left it, every time we expect a moving object to continue along a path, we are betting on inertia. Society itself depends on this bet. Transportation, construction, engineering, and technology all assume inertial behavior as a given. If inertia were to fail even briefly, chaos would follow. At a deeper philosophical level, inertia shapes our understanding of causality. It enforces the idea that effects require causes. Motion does not spontaneously change. Something must act. This principle is so ingrained that it feels obvious, yet it is entirely contingent on inertia being true. In a universe without inertia, events could unfold without reason, and explanation would lose meaning. Feynman's way of explaining inertia as fundamental was ultimately an invitation to curiosity rather than closure. He did not present inertia as a solved mystery, but as a beautifully described one. We know what it does. We know how to measure it. We know it never fails. But we do not know why the universe chose this rule. That unanswered why is not a flaw, it is fuel for science. By the time one fully absorbs inertia in this way, it no longer feels like a simple law memorized in school. It becomes a quiet pillar holding up the entire structure of physical understanding. Every force, every motion, every calculation leans on it. Inertia is not dramatic, but it is decisive. It tells us that the universe values continuity, consistency, and restraint. In the end, to say that inertia is a fundamental property of matter is to say that matter has an inherent loyalty to its present state. Change is possible, but it must be earned. That single idea, repeated endlessly from particles to planets, is one of the deepest insights physics has ever uncovered. When examining why objects resist changes in motion, Richard Feynman encouraged people to abandon the idea that resistance comes from stubbornness, fatigue, or any hidden internal struggle. Instead, he framed this resistance as one of the most reliable behaviors observed in nature. Objects do not oppose change because they are fighting back. They resist change simply because that is how matter behaves. This resistance is not emotional, mechanical, or psychological. It is a measurable, repeatable fact. At first glance, the idea seems almost trivial. When you try to push a heavy object, it is harder to get it moving. When something is already moving fast, it is harder to stop. Most people accept this without thought. Feynman insisted that this familiarity is precisely the problem. Familiarity hides the strangeness of the phenomenon. The question is not whether objects resist changes in motion, but why the universe is constructed so that they must. The resistance to changes in motion appears equally whether the change involves starting, stopping, speeding up, slowing down, or turning. This universality is crucial. It tells us that inertia does not favor any particular state. Rest is not special. Motion is not special. What matters is change. Any deviation from the current state of motion is met with resistance. The object behaves as if it prefers continuity, though preference is only a metaphor. Feynman was careful to point out that this resistance is not caused by external obstacles unless we can clearly identify them. Friction, air resistance, and internal deformations complicate motion, but they are not the source of inertial resistance. Even in their absence, resistance to acceleration remains. This is why astronauts in space still feel resistance when pushing tools or moving equipment, even though friction is nearly eliminated. The resistance comes from inertia itself. One of the key insights Feynman emphasized is that resistance to motion change is symmetric in time. An object resists being accelerated forward just as strongly as it resists being decelerated. It resists being turned sideways just as strongly as it resists being sped up or slowed down. This symmetry shows that inertia does not care about direction or outcome. It only responds to attempts at alteration. This resistance becomes especially clear when forces are applied suddenly. A quick jerk on an object produces a stronger feeling of resistance than a slow, steady pull. The object is not reacting to speed, but to acceleration, to the rate at which you are trying to change its motion. Feynman loved this distinction because it reveals something subtle. Objects do not resist motion, they resist acceleration. Motion itself is free. Change is costly. This insight reshapes how we understand effort. When lifting a heavy object slowly, the effort feels manageable. Try to lift it suddenly, and the resistance feels much greater. The object has not changed. The force of gravity has not changed. What has changed is how quickly you are trying to alter its state of motion. Inertia responds immediately and proportionally. Feynman often warned against imagining inertia as a hidden force pushing back. There is no counter force generated by the object simply because it has inertia. Instead, inertia defines how much acceleration results from a given force. If you apply a small force, the change in motion is small. Apply a larger force, and the change is larger. The resistance is not an active opposition but a passive rule governing response. This distinction matters deeply. If inertia were an active opposing force, motion would behave very differently. Objects might overshoot, oscillate, or behave unpredictably. Instead, the relationship between force and acceleration is clean and linear. The universe behaves with remarkable discipline. Feynman admired this simplicity, seeing it as evidence that nature follows rules that are not only consistent but elegant. The resistance to changes in motion also reveals itself in collisions. When two objects collide, both resist changes in their motion. The outcome depends on how much inertia each object has. A small object colliding with a massive one changes its motion dramatically, while the massive object changes very little. This is not because the larger object is stronger or more rigid, but because it has greater inertia. Motion is redistributed according to resistance to change. Feynman emphasized that this behavior holds regardless of what the objects are made of. Steel, wood, plastic, gas, or plasma all resist changes in motion according to their mass. Composition affects strength, elasticity, and other properties, but inertia depends only on how much mass is present. This independence from material details is a powerful clue that inertia is fundamental rather than accidental. At the microscopic level, the same resistance appears. Atoms resist acceleration, electrons resist acceleration. Even particles with no internal structure that we can detect still resist changes in motion. This consistency across scales reinforces the idea that inertia is not built from smaller mechanisms. It is present at every level we can observe. Feynman often challenged people to consider how strange this is. Why should the amount of matter determine how difficult it is to change motion? Why should doubling the mass double the resistance? There is no intuitive reason, it simply happens. Experiments confirm it with astonishing precision. The universe behaves as if it is keeping careful accounts, ensuring that resistance to change scales exactly with mass. This resistance also explains why forces must act continuously to maintain acceleration. If you want to keep increasing an object's speed, you must keep applying force. The moment you stop, acceleration ceases. Motion continues, but change stops. This sharp distinction between motion and acceleration is one of the hardest ideas for beginners to grasp, yet it sits at the heart of inertia. Feynman used everyday examples to break this mental barrier. When driving a car, pressing the accelerator does not add motion in a vague sense. It applies a force that changes motion. Let go of the pedal, and the car does not instantly stop accelerating because of inertia. It stops accelerating because the force has been removed. The continued motion afterward is inertia expressing itself. The resistance to changes in motion also clarifies why prediction works so well in physics. Because objects respond to forces in predictable ways, we can calculate future motion from present conditions. If resistance varied unpredictably, planning would be impossible. Inertia provides stability not just to objects, but to knowledge itself. Feynman was especially interested in how this resistance underpins conservation laws. Momentum remains constant unless acted upon because objects resist changes in motion. Energy calculations rely on this resistance being reliable. Without inertia, the careful balance seen in physical interactions would collapse into unpredictability. Inertia's resistance to change also plays a central role in safety and engineering. Seatbelts exist because bodies resist sudden changes in motion. Buildings are designed with inertia in mind to withstand earthquakes and wind. Machines are built to manage inertial loads, so they do not tear themselves apart. All of this practical knowledge rests on the same fundamental principle. From a broader perspective, resistance to changes in motion shapes the character of the universe. It enforces continuity. It prevents spontaneous chaos. Things do not suddenly reverse direction or speed up without cause. Events unfold smoothly unless acted upon. This smoothness allows complex structures to form and persist. Feynman often highlighted that this resistance is not negotiable. No object has ever been observed to violate it. No matter how extreme the conditions, inertia holds. Even near the limits of known physics, where energy is enormous and distances are tiny, resistance to acceleration remains a defining feature. At a philosophical level, resistance to change mirrors a deeper theme in nature. Stability dominates unless disrupted. Change is possible, but it is never free. This idea resonates beyond physics, but in physics it is precise and measurable. Inertia is not a metaphor here. It is a numerical relationship tested again and again. As one reflects on why objects resist changes in motion, it becomes clear that this resistance is not an inconvenience or a complication. It is the reason motion makes sense at all. Without resistance, forces would produce wild, uncontrollable effects. With resistance, the universe becomes intelligible. Feynman's explanation strips away mystery without destroying wonder. We may not know why the universe chose inertia, but we can see how deeply it shapes everything. Every push, every stop, every turn carries the same signature. Matter does not surrender its state of motion without a reason. In the end, the resistance of objects to changes in motion is not a flaw in nature. It is one of its greatest strengths. It provides order, predictability, and coherence. It ensures that causes lead to effects in stable ways. It allows motion to be understood, harnessed, and trusted. Understanding this resistance is not just learning a law of physics. It is learning how the universe expresses restraint. Motion persists. Change must be justified. That single rule echoes through every interaction we observe, quietly governing the behavior of all matter. To continue exploring why objects resist changes in motion, Richard Feynman pushed the discussion toward a more subtle and often overlooked realization. Resistance to change is not something added on top of motion. It is inseparable from how motion is defined in the first place. Motion without inertia would not merely look different, it would lose coherence. Inertia is what gives motion continuity, allowing the universe to evolve smoothly instead of jumping unpredictably from one state to another. Feynman often explained that when we feel resistance, we are actually sensing the cost of altering a perfectly valid state of nature. An object moving at constant speed in a straight line is not in a weaker or less complete condition than one at rest. Both states are equally legitimate. When we try to change either one, we are attempting to force the universe away from a condition it already fully accepts. Inertia is the rule that enforces this acceptance. This idea becomes clearer when we think about sudden versus gradual changes. A gentle push produces a gentle response, while a sharp push produces a strong resistance. The object is not responding to motion itself, but to how violently we are attempting to rewrite its current state. In this way, inertia acts like a natural regulator. It prevents abrupt, discontinuous behavior unless equally abrupt forces are applied. Feynman emphasized that this resistance is instantaneous. The moment a force is applied, inertia defines the response. There is no delay, no buildup, no hesitation. This immediacy is crucial. It shows that inertia is not a process unfolding over time, but a condition that exists at every moment. At each instant, matter answers the question, how much should I change my motion given this force? The answer is always the same relationship. This leads to a deeper appreciation of acceleration as the central concept. Most people focus on speed, but inertia does not care how fast something is moving. An object moving slowly and one moving extremely fast behave identically when the same force is applied, provided their masses are the same. What matters is not motion itself, but the attempt to alter it. Inertia responds only to acceleration. Feynman found this deeply counterintuitive and deeply beautiful. It means that an object moving steadily through space is, in a sense, already in harmony with the universe. There is no internal stress, no tendency to change. Only when an external influence appears does inertia reveal itself. This makes inertia a silent property, invisible until challenged. The resistance to change also explains why forces can be measured by their effects rather than by any intrinsic signature. We do not see forces directly. We infer them from acceleration. If inertia were inconsistent, force measurement would be unreliable. The fact that inertia behaves identically everywhere allows force to be defined operationally. Push something, observe how its motion changes, and you know how strong the force is. Feynman often reminded audiences that this reliability is not guaranteed by logic, it is an empirical fact. The universe did not have to cooperate. Resistance to change could have depended on shape, temperature, color, or history. Instead, it depends only on mass. This simplicity is astonishing. It suggests that inertia is not a surface-level phenomenon, but a deep organizing principle. At higher speeds and energies, resistance to change becomes even more revealing. As objects approach extreme conditions, their response to force becomes more complex, yet the core idea survives. They still resist changes in motion. Even when classical descriptions fail, inertia does not disappear. It adapts, but it remains central. Feynman admired how this single idea survives radical shifts in theoretical framework. Resistance to change also clarifies why motion cannot be created or destroyed arbitrarily. You cannot simply decide that an object should be moving faster and expect it to happen. Something must act, and that action must overcome inertia. This requirement anchors motion in causality. It ensures that every change can be traced back to an interaction. Feynman liked to highlight that inertia makes the universe economical. Nothing happens without reason. Nothing changes without cause. This economy allows patterns to persist long enough to be studied. Without resistance to change, atoms would not form stable structures, planets would not maintain orbits, and complex systems would not endure. The same resistance that makes pushing a heavy object difficult also makes precision possible. Machines rely on inertia to smooth motion, to store energy, and to maintain stability. A spinning flywheel resists changes in speed and orientation, providing consistency. This is inertia at work, quietly enforcing regularity. In everyday life, inertia's resistance is often mistaken for inconvenience. We complain that heavy things are hard to move, that vehicles take time to stop, that sudden motions feel uncomfortable. Feynman reframed this frustration as evidence of reliability. The same resistance that makes sudden changes difficult is what prevents sudden disasters. It gives us time to react. It makes motion predictable. Resistance to change also explains why motion feels relative. Because inertia treats constant motion as equivalent to rest, there is no experiment you can perform inside a smoothly moving system to detect that motion. This insight reshaped physics and laid the groundwork for later developments. Inertia erases absolute motion, leaving only relative change. Feynman emphasized that this equivalence is not philosophical speculation but experimental fact. Every attempt to detect absolute uniform motion has failed. Objects resist changes, not states. This forces us to abandon the idea of a preferred state of rest. Inertia insists on neutrality. The deeper one goes, the more resistance to change appears as a unifying theme. It links mechanics, astronomy, engineering, and modern physics. It explains why conservation laws hold and why symmetry matters. Resistance to change is the backbone of predictability. Feynman also pointed out that inertia is not something objects can lose. Heating an object, cooling it, compressing it, or reshaping it does not eliminate inertia. Only changing the amount of matter changes resistance. This permanence reinforces the idea that inertia is not an emergent convenience, but an intrinsic attribute. At the human scale, resistance to change shapes experience. Sudden stops feel violent, gradual changes feel manageable. Our bodies made of matter obey the same rule. We are not separate from physics, we are expressions of it. Inertia governs our sensations as much as it governs stars. Feynman's teaching style made people aware that resistance to change is not a limitation imposed on matter, but a guarantee offered by the universe. It guarantees that the present has continuity with the past. It guarantees that tomorrow follows from today. In the absence of resistance, motion would be meaningless. Any force, no matter how small, could cause infinite acceleration. The universe would be unstable. Structures could not exist. Resistance to change is what prevents this absurdity. When seen this way, inertia becomes a form of restraint written into nature. It says that change must be proportional to cause. It enforces fairness. Small causes produce small effects. Large causes produce large effects. This proportionality is the foundation of understanding. Feynman often left audiences with a sense that inertia is less about objects and more about rules. Objects follow rules they did not choose. Resistance to change is one of those rules. It does not explain itself, but it explains everything else. By the end of this deeper reflection, resistance to changes in motion no longer feels like a mechanical detail. It feels like a statement about how reality values continuity. Motion is allowed. Change is permitted. But nothing happens without a reason. That is the quiet power of inertia. It does not announce itself loudly, but it governs every movement, every collision, every trajectory. Objects resist changes in motion not out of stubbornness, but because the universe itself insists on order. When exploring the connection between inertia and mass, Richard Feynman insisted that this relationship is not a convenient definition invented by physicists, but a deep empirical discovery about how the universe behaves. Mass is not merely the amount of material in an object in some vague sense. It is a precise measure of how strongly that object resists changes in its motion. In this view, mass and inertia are not separate concepts tied together by coincidence. They are two faces of the same underlying property of matter. Feynman emphasized that whenever we talk about mass in physics, we are really talking about inertia. If an object has more mass, it does not just weigh more under gravity, it also accelerates less when pushed by the same force. This resistance to acceleration is not an added feature of mass. It is what mass means operationally. You know an object's mass by how difficult it is to change its motion. There is no deeper mechanical definition hiding underneath. This idea becomes clear the moment gravity is removed from the discussion. In everyday life, people associate mass with heaviness. A heavy object is hard to lift, so it feels massive. But Feynman was careful to strip gravity away to reveal what mass truly represents. In deep space, far from planets and stars, objects are weightless. Yet they still resist being pushed. An astronaut pushing a large tool experiences resistance, not because of weight, but because of inertia. That resistance is mass revealing itself in its purest form. Feynman liked to stress that this distinction is crucial. Weight depends on gravity. Mass does not. Mass exists even in the absence of gravitational fields. It is a property of the object itself, not of its environment. This universality is one of the strongest clues that inertia and mass are fundamentally linked. When a force is applied to an object, the resulting acceleration depends on the object's mass. Double the mass, and the same force produces half the acceleration. This proportionality is exact. It has been tested across enormous ranges of scale and energy. Feynman often marveled at how precise this relationship is. Nature does not approximate it, it enforces it strictly. The connection between inertia and mass also reveals why mass is additive. Combine two identical objects, and the combined system has twice the inertia. It resists acceleration twice as much. This additivity is not obvious a priori. It could have been otherwise. Matter could have exhibited strange collective behavior where combined objects responded unpredictably. Instead, inertia adds cleanly. This simplicity allows mass to be measured, compared, and conserved. Feynman also emphasized that mass does not care about shape, composition, or internal complexity. A block of iron and a block of wood with the same mass respond identically to applied forces when friction and other effects are removed. This indifference shows that inertia is blind to internal details. Whatever is going on inside matter, inertia summarizes its response to force in a single number mass. At the microscopic level, this relationship persists. Individual particles have mass, and that mass determines how they accelerate under forces. Even particles that seem point-like and structureless exhibit inertia. They do not escape this rule by being small. In fact, the precision with which particle masses and inertial responses can be measured is one of the triumphs of modern physics. Feynman often pointed out how strange it is that mass plays this dual role. On one hand, it measures resistance to acceleration. On the other hand, it determines how strongly an object interacts gravitationally. The same quantity that resists motion change also controls gravitational attraction. This equivalence is not explained by classical physics, it is simply observed. That observation, however, has enormous consequences. This equivalence led to profound developments in physics. But even without invoking advanced theory, the mystery remains. Why should the thing that makes objects hard to accelerate also make them sources of gravity? Feynman did not pretend this question had a simple answer. He treated it as one of nature's remarkable coincidences, one that hints at deeper unity. Returning to inertia, Feynman emphasized that mass is not a measure of how much an object moves, but how much it refuses to change how it moves. A massive object is not one that moves more, but one that changes less under the same influence. This inversion of intuition is subtle. People often think mass is about substance or size. In physics, it is about response. This way of thinking reshapes how we understand force. Force does not directly cause motion, it causes acceleration, and how much acceleration results depends on mass. Inertia, quantified by mass, moderates every interaction. Without mass, forces would have no meaningful effect. With mass, forces produce controlled, proportional changes. Feynman also highlighted that mass sets the scale of physical experience. A small force can noticeably change the motion of a light object, but barely affects a massive one. This difference underlies everything from the way dust floats in air to the way planets move through space. The same laws apply, but mass determines how visible the effects are. One of the most striking demonstrations of the inertia-mass connection is found in collisions. When two objects collide, their masses determine how their motions change. A light object bouncing off a heavy one reverses direction dramatically, while the heavy object barely notices. This asymmetry is not about strength or rigidity, it is pure inertia. The more massive object resists change more strongly. Feynman often warned against confusing inertia with hardness or durability. A fragile object can have large mass and strong inertia. A very hard object can have small mass and weak inertia. Inertia has nothing to do with how easily something breaks. It has everything to do with how motion responds to force. At higher energies, mass becomes even more intriguing. As objects move faster and faster, their resistance to further acceleration increases. While the details belong to more advanced physics, the core idea remains the same: inertia is tied to mass, and mass governs response to force. Even when descriptions change, the principle survives. Feynman's teaching style made people appreciate that mass is not an abstract label. It is something you can feel. Every time you push an object and sense resistance, you are directly interacting with its mass. This tactile experience is rare in physics, where many quantities are invisible. Mass announces itself through inertia. The connection between inertia and mass also explains why mass is conserved in ordinary interactions. If mass were not conserved, resistance to motion change would fluctuate unpredictably. Objects would accelerate differently at different times for no apparent reason. The conservation of mass stabilizes inertia, ensuring consistent behavior. Feynman emphasized that this consistency is not trivial. It allows engineers to design machines, physicists to predict motion, and astronomers to model the universe. The inertia-mass connection is a pillar supporting all of classical mechanics. At a deeper level, this connection also sets limits. Because mass resists acceleration, no object can be accelerated infinitely fast by a finite force. This restraint protects the universe from absurd behavior. It enforces proportionality between cause and effect. Feynman often returned to the idea that physics does not explain mass in the everyday sense of why. We can measure it, compare it, and use it, but we do not know why matter has mass at all. Yet this ignorance does not weaken the concept, it sharpens it. Mass becomes one of those fundamental facts about the universe that simply must be accepted as a starting point. By tying inertia directly to mass, Feynman removed any temptation to treat inertial as an optional or secondary concept. It is central. It defines mass and mass defines it in return. Together, they form a closed loop of meaning that anchors motion in measurable reality. In the end, understanding the connection between inertia and mass changes how one sees matter itself. Matter is not passive substance waiting to be moved. It is active in its resistance. It participates in motion by limiting how motion can change. This participation is quantified by mass. Through this lens, mass becomes more than a number in an equation. It becomes the universe's way of enforcing continuity. It ensures that objects do not respond wildly to small influences. It gives motion stability and predictability. Feynman's explanation leaves us with a powerful realization: every object carries within it a built-in reluctance to change its motion, and that reluctance is what we call mass. Wherever matter exists, inertia follows. Wherever inertia is measured, mass is revealed. This insight transforms mass from a static concept into a dynamic one. It is not just how much matter there is, but how that matter behaves when the universe tries to push it into something new. Continuing deeper into the connection between inertia and mass, Richard Feynman often guided attention toward an idea that at first feels unsettling: mass is not something we truly see in the world, but something we infer entirely from behavior. We never observe mass directly. What we observe is resistance. We push, pull, collide, accelerate, and decelerate objects, and from how strongly they resist these changes, we assign a number called mass. In this sense, mass is not a visual or material quantity, but a behavioral one. Feynman stressed that this makes mass fundamentally different from properties like color, shape, or texture. Those properties can be perceived immediately. Mass reveals itself only through interaction. An object sitting quietly tells you nothing about its mass until you try to change its motion. Only then does inertia speak. This makes mass inseparable from dynamics. Without motion or attempted motion, mass would be meaningless. This realization reframes how we think about matter itself. Matter is not defined by how it looks or even by how much space it occupies, but by how it responds to force. Two objects may appear completely different, but if they respond identically to applied forces, physics treats them as having the same mass. This abstraction is powerful. It strips away surface details and focuses on what nature consistently preserves. Feynman often pointed out that this perspective explains why mass became such a central quantity in physics so early. Long before atoms were understood, people could tell that some objects were harder to move than others. This resistance was measurable and repeatable. Even without knowing anything about internal structure, inertia could be compared. Mass emerged as one of the first truly quantitative ideas about matter. The connection between inertia and mass also explains why mass sets the scale for how forces matter. A force that is dramatic for a light object may be negligible for a massive one. This relative effect is not a property of the force itself, but of the object's inertia. Force has meaning only in relation to mass. Without mass, force would have no context. Feynman emphasized that this relationship makes mass a mediator between cause and effect. Force is the cause. Acceleration is the effect. Mass sits between them, regulating how strongly the cause translates into the effect. This mediation ensures proportionality. It prevents tiny causes from producing enormous, uncontrolled changes. This proportionality is one of the reasons physics is mathematically stable. Equations of motion work because mass behaves consistently. If mass varied unpredictably or depended on hidden factors, motion would be chaotic. The fact that mass is stable allows the universe to be intelligible. Feynman also explored how the inertia-mass connection reveals itself in systems rather than individual objects. When objects are connected, their masses combine to determine the inertia of the system as a whole. Push a cart carrying a load, and you feel the inertia of both together. This shows that mass is not confined to isolated objects. It is a property that extends to any collection of matter acting as a unit. This system-level behavior reinforces the idea that mass is additive and transferable. When matter moves together, inertia moves with it. There is no hidden loss or gain. The resistance to acceleration simply reflects how much matter is participating in the motion. At a deeper level, Feynman liked to highlight that mass defines how much an object contributes to the inertia of the universe. Every piece of matter adds its share of resistance to change. This idea hints at a collective aspect of inertia. While inertia is measured locally, it is universal in scope. Everywhere matter exists, resistance to motion change exists. The equivalence between inertial mass and gravitational mass adds another layer of mystery. Objects that resist acceleration also respond more strongly to gravity. This fact is not obvious, yet it is exact. Feynman often emphasized that classical physics cannot explain this equivalence. It is an empirical truth, and its precision is astonishing. This equivalence suggests that mass is not merely a local property of objects, but something deeply connected to the structure of space and interaction. Even without invoking advanced theories, one can sense that inertia and gravity are not unrelated accidents. They are linked expressions of mass. Returning to everyday experience, Feynman liked to remind people that mass is felt most clearly when motion changes abruptly. Sudden stops, sharp turns, rapid accelerations all make inertia obvious. The discomfort we feel in such moments is not caused by motion, but by attempts to change motion. Our own bodies resist acceleration just like any other object. This bodily experience is crucial. It grounds the concept of mass in sensation. When you feel thrown forward during sudden braking, you are not feeling speed. You are feeling inertia. Your mass resists the change imposed by the vehicle. This makes mass one of the few physical quantities that humans can feel directly. Feynman used this to emphasize that physics is not detached from experience. The laws governing stars and particles also govern muscles, bones, and organs. We are made of matter, and mass governs our motion as faithfully as it governs anything else. The inertia-mass connection also explains why energy transfer is limited. To change the motion of a massive object significantly, a large amount of energy is required. This requirement protects structures from instability. Buildings do not collapse from small disturbances. Planets do not suddenly change orbits. Mass provides inertia that dampens the effects of small influences. Feynman pointed out that without this damping, the universe would be violently unstable. Tiny fluctuations could lead to enormous motions. Nothing would persist long enough to form complex structures. Mass, through inertia, provides a kind of physical patience. At the same time, mass does not prevent change altogether. With sufficient force, any object can be accelerated. Inertia does not forbid change, it regulates it. This balance between resistance and responsiveness allows both stability and dynamism. The universe can evolve without dissolving into chaos. Feynman often highlighted that this balance is remarkably well tuned. Forces in nature are strong enough to overcome inertia when needed, but not so strong that inertia becomes irrelevant. The interplay between force and mass shapes everything from atomic vibrations to galactic motion. Another subtle point Feynman emphasized is that mass defines identity over time. Because inertia resists sudden change, an object's motion evolves smoothly. This smooth evolution allows us to track objects, predict their paths, and identify them as the same objects from moment to moment. Without inertia, identity would blur. In collisions, mass determines how motion is redistributed. This redistribution follows strict rules, reflecting inertia at work. These rules are not arbitrary. They arise because mass governs how strongly each object can change. This makes collisions predictable rather than chaotic. Feynman also explored how mass relates to momentum. Momentum combines mass and velocity, capturing how much motion an object carries. Inertia ensures that momentum is conserved unless acted upon. This conservation is not an extra rule layered on top of inertia, it is a direct consequence of it. Through momentum, mass influences interactions, even when objects are not in direct contact. Fields transfer momentum, and mass determines how motion changes in response. Inertia remains the underlying regulator. Feynman cautioned against thinking of mass as stuff packed into an object. Modern physics suggests that mass can arise from energy, interactions, and fields. Yet regardless of origin, mass always manifests as inertia. No matter how mass is generated, its role in resisting acceleration is universal. This universality makes inertia a unifying concept. It links classical mechanics, modern physics, and everyday experience. Even as theories evolve, inertia remains a constant feature. It is reinterpreted, but never discarded. Feynman's approach was not to eliminate mystery, but to clarify where mystery truly lies. The inertia-mass connection is well described, precisely measured, and universally observed. What remains mysterious is why it exists at all. That mystery does not weaken the concept, it elevates it. By understanding mass as inertia, we shift from thinking of mass as passive quantity to seeing it as an active participant in motion. Matter does not merely move when pushed. It responds according to a built-in rule that limits how motion can change. This perspective transforms how we see the physical world. Objects are not just carriers of motion, they are regulators of motion. Their mass determines how they negotiate with forces. In the end, the connection between inertia and mass reveals a profound simplicity. One number summarizes an object's resistance to change. That number governs acceleration, collisions, stability, and motion across the universe. Feynman's insight makes mass feel less like an arbitrary label and more like a statement about nature's character. The universe does not allow motion to be rewritten cheaply. It demands payment in force, and the price is set by mass. Through this lens, inertia and mass are inseparable expressions of a single principle. Matter carries with it a built-in resistance to change, and that resistance is precisely what gives the universe order, predictability, and continuity. When discussing inertia in relation to Newton's laws of motion, Richard Feynman made it clear that these laws are not independent rules stacked on top of one another, but different perspectives on the same underlying behavior of matter. Inertia is not merely mentioned in Newton's first law, it is the quiet assumption that gives meaning to all three. Without inertia, the laws would lose their coherence and their power to describe reality. Newton's first law states that an object remains at rest or moves in a straight line at constant speed unless acted upon by a force. Feynman emphasized that this law is not a consequence of the other two, nor is it an obvious truth. It is a declaration about how nature behaves when nothing interferes. The law identifies inertial motion as the default condition of the universe. It tells us what happens when forces are absent, which is essential because it defines what we mean by a force in the first place. Feynman often pointed out that the first law serves as a kind of reference point. It defines inertial frames of motion, frames in which objects obey this rule of unchanging motion. Only after establishing this baseline does it make sense to talk about forces and acceleration. Without inertia, there would be no clear distinction between natural motion and forced motion. Everything would blur together. The second law then quantifies inertia. It connects force, mass, and acceleration in a precise way. Feynman stressed that this law does not say force causes motion, but that force causes a change in motion, and that change depends on inertia. The law only works because objects resist changes in motion. If there were no inertia, any force, no matter how small, would produce infinite or unpredictable acceleration. The linear relationship between force and acceleration exists because inertia moderates the response. This makes the second law an operational statement. You can measure force by observing how much acceleration it produces in an object of known mass, but this only works because inertia behaves consistently. Mass, as a measure of inertia, ensures that the same force produces the same acceleration every time under the same conditions. Feynman admired how this reliability turns abstract laws into practical tools. The third law, stating that for every action there is an equal and opposite reaction, also rests on inertia. When two objects interact, both resist changes in motion. The forces they exert on each other are equal because each object's inertia governs how it responds. Motion is redistributed, not created or destroyed. Inertia ensures that interactions are mutual rather than one-sided. Feynman often explained that the third law is easiest to misunderstand because people imagine forces as one object actively pushing another. In reality, interactions are exchanges governed by inertia. When you push on a wall, the wall pushes back, not because it is alive or reactive, but because its inertia resists being accelerated. The force you feel is the manifestation of that resistance. Together, the three laws form a unified picture. The first law defines inertial motion. The second law explains how inertia regulates changes in motion. The third law shows how inertia enforces balance in interactions. Remove inertia from this picture, and the structure collapses. Forces lose meaning, acceleration becomes arbitrary, and interaction loses symmetry. Feynman also emphasized that Newton's laws are not self-evident truths. They are distilled from observation. The fact that inertia exists and behaves as it does is an empirical discovery. The laws work because the universe cooperates, not because logic demands it. This humility was central to Feynman's teaching. Physics describes what nature does, it does not dictate what nature must do. Inertia's role in Newton's laws also explains why motion can be described so simply over vast ranges of scale. The same laws apply to falling apples, moving vehicles, orbiting planets, and spacecraft traveling between worlds. Inertia does not weaken with size or distance. It applies uniformly. This universality is what allowed Newton's laws to dominate physics for centuries. Feynman often highlighted that even when later theories expanded or refined Newton's framework, inertia remained central. The language changed, the mathematics deepened, but the idea that objects resist changes in motion survived. This persistence shows that inertia is not an artifact of a particular theory, but a real feature of the world. Another subtle point Feynman raised is that Newton's first law is often misunderstood as redundant. Some textbooks suggest it follows from the second law by setting force to zero. Feynman rejected this view. Without the first law, there is no guarantee that zero force corresponds to constant velocity. The first law asserts that correspondence. It establishes the meaning of no force by describing inertial behavior. This clarification reveals how deeply inertia is woven into the logical structure of mechanics. It is not just a topic within mechanics. It is the foundation on which mechanics is built. Newton's laws are not laws about force alone, they are laws about how inertia constrains motion. Feynman also used Newton's laws to show that inertia removes any need for absolute rest. Because inertial motion includes constant velocity, there is no preferred state of being still. All inertial frames are equally valid. This insight reshaped physics and later became crucial for deeper theories. Inertia forces us to abandon the idea that the universe has a natural center or a special state of rest. In practical terms, Newton's laws allow engineers and scientists to predict motion with extraordinary accuracy because inertia behaves consistently. Bridges stand, vehicles move, machines operate, and planets orbit because inertia responds to force in reliable ways. Every calculation assumes that objects will not surprise us by suddenly changing motion without cause. Feynman liked to emphasize that this predictability is not boring. It is miraculous. The universe could have been erratic. Instead, inertia gives it discipline. Newton's laws capture that discipline in concise statements. In the end, inertia's role in Newton's laws reveals a deep truth: motion is not something fragile that must be constantly sustained. It is the natural state. Forces exist to change motion, not to maintain it. Newton's laws, guided by inertia, express this truth with clarity and power. Through Feynman's lens, Newton's laws are not just equations to be memorized. They are insights into how nature prefers continuity over chaos. Inertia is the quiet rule that makes those insights possible, anchoring motion to reason and making the universe intelligible. When inertia is examined through everyday examples, Richard Feynman believed it becomes more than an abstract scientific principle and turns into something immediately recognizable. He often emphasized that the best way to understand inertia is not by memorizing laws, but by paying close attention to ordinary experiences that people usually dismiss as trivial. These familiar moments are where inertia reveals itself most clearly. One of the simplest examples occurs when a vehicle suddenly stops. Passengers feel their bodies thrown forward, even though nothing is pushing them in that direction. Feynman stressed that this sensation is not caused by a mysterious forward force. It happens because the body was already moving, and inertia carries it forward when the vehicle decelerates. The seatbelt exists precisely because inertia is reliable. It restrains the body, forcing it to change motion along with the vehicle. Another everyday example appears when a vehicle starts moving suddenly. Passengers feel pushed backward into their seats. Again, there is no backward force acting on the body. The body simply resists the change from rest to motion. The seat pushes the person forward, and inertia resists that acceleration. What people interpret as being pushed back is actually the body's reluctance to begin moving. Feynman liked to point out that these sensations are so common that people rarely question them. Yet they are direct physical demonstrations of inertia at work inside the human body. Muscles, organs, and bones all obey the same rules as any other matter. The discomfort felt during sudden motion changes is inertia being felt directly. A similar effect can be seen when carrying a cup of water. If you start walking suddenly, the water sloshes backward. If you stop suddenly, it sloshes forward. The water is not reacting to your intention. It is obeying inertia, maintaining its current state of motion while the container changes speed. This simple observation shows how inertia acts independently of human control. Feynman often used tablecloth and coin tricks to illustrate the same idea. When a tablecloth is pulled quickly from under dishes, the dishes remain nearly in place. Their inertia resists the sudden horizontal motion. If the cloth is pulled slowly, friction has time to act, and the dishes move along. This contrast reveals the competition between inertia and external forces. Another classic example involves a coin placed on a card over a glass. When the card is flicked away quickly, the coin drops straight down into the glass. The coin resists horizontal motion due to inertia, while gravity pulls it downward. This experiment isolates inertia in a simple, memorable way. Feynman emphasized that sports are full of inertial examples. A ball thrown from a moving vehicle continues to move forward relative to the ground, not simply drop straight down. Athletes instinctively account for inertia when catching, throwing, or hitting objects. They may not use the word, but their actions show an intuitive understanding of resistance to motion change. In everyday walking, inertia is constantly managed without conscious thought. When turning a corner, the body leans inward. This is not because the body wants to fall, but because inertia resists the change in direction. Leaning allows forces to redirect motion safely. Feynman loved pointing out how the body naturally adapts to inertial effects without formal training in physics. In the kitchen, inertia appears when stirring liquids. stops stirring suddenly, and the liquid continues moving, creating swirls and eddies. The liquid resists the sudden change imposed by the spoon. These motions fade only when friction and viscosity dissipate the energy. Inertia keeps the motion alive until external forces intervene. Household objects also demonstrate inertia when moved abruptly. Pulling a rug quickly can cause objects on it to lag behind or topple. The objects resist the sudden acceleration of the rug. The same action performed slowly produces a different outcome, highlighting how inertia responds to acceleration rather than speed. Feynman often reminded people that inertia explains why sudden changes feel more dramatic than gradual ones. Sudden braking is uncomfortable, gradual braking is tolerable. Sudden lifting strains muscles, slow lifting feels easier. The difference lies not in the final state, but in how quickly motion is altered. Inertia responds to rapid change. Everyday accidents often involve inertia misunderstood or ignored. Items in a car become dangerous projectiles during sudden stops because they continue moving forward. This is why loose objects must be secured. Feynman used such examples to show that inertia is not merely academic. It has practical consequences for safety. Children experience inertia vividly when running and trying to stop quickly. They may stumble or fall because their bodies continue moving forward. Learning to anticipate inertia is part of developing coordination. The same principle applies to adults in more complex activities. Feynman liked to point out that even standing still on Earth involves inertia in a subtle way. The planet is rotating and orbiting the sun, yet we do not feel these motions because they are nearly constant. Inertia makes constant motion indistinguishable from rest in everyday experience. Only changes, like turbulence or acceleration, become noticeable. This insight explains why elevators feel strange when they start or stop, but not while moving steadily. During constant speed, inertia is satisfied. When acceleration occurs, inertia resists, and we feel weight changes. These sensations are direct consequences of inertia interacting with gravity. In tools and machines, inertia appears in spinning parts. A rotating fan resists changes in speed and orientation. Turn it off, and it keeps spinning. Try to stop it suddenly, and you feel resistance. Engineers design machines with inertia in mind to ensure smooth operation and prevent damage. Feynman emphasized that everyday examples are powerful because they strip away abstraction. They show that inertia is not hidden in equations. It is present in ordinary life, shaping experience constantly. The laws of physics are not confined to laboratories, they operate everywhere, all the time. By reflecting on these examples, one begins to see inertia not as a strange scientific idea, but as a familiar companion. Every movement, every stop, every turn involves it. Understanding inertia through daily life builds intuition that supports deeper study. Feynman believed that when people recognize inertia in their own experiences, physics becomes less intimidating and more honest. It is no longer about memorizing formulas, but about understanding the rules that govern what we already feel and see. In the end, everyday examples reveal inertia as something intimate. It affects comfort, safety, coordination, and motion at every scale of daily life. These examples do not simplify inertia, they reveal its true significance. Through them, inertia becomes not just a principle of motion, but a constant presence, quietly shaping how we move through the world and how the world moves around us. When inertia is examined from the atomic and microscopic point of view, Richard Feynman encouraged listeners to let go of the idea that inertia somehow emerges only at large scales. One of his most consistent messages was that nature does not change its rules just because we look more closely. The same resistance to changes in motion that governs cars, planets, and people also governs atoms, electrons, and every particle we can observe. At the microscopic level, inertia becomes even more striking because many of the familiar sources of resistance disappear. There is no air resistance inside an atom. There is no surface friction between elementary particles. Yet when forces act, particles still resist acceleration in a precise, measurable way. This alone shows that inertia is not caused by environmental drag or mechanical rubbing. it is intrinsic to matter itself. Feynman often highlighted that particle accelerators provide some of the clearest demonstrations of inertia. In these machines, particles are pushed by electromagnetic forces to extremely high speeds. The harder scientists push, the more resistance they encounter. The particles do not suddenly accelerate wildly. Their response follows strict rules governed by inertia. These experiments are conducted in near-perfect vacuums, eliminating common sources of resistance, yet inertia remains fully present. At the atomic scale, electrons orbit nuclei, not because they are being constantly forced to move forward, but because their inertia carries them along while forces bend their paths. This mirrors planetary motion on a vastly smaller scale. The same principle applies: inertia maintains motion, forces redirect it. Feynman loved pointing out this symmetry across scales because it reveals a deep unity in nature. Even when classical pictures break down, inertia does not vanish. In quantum physics, particles do not follow simple trajectories, yet their response to applied forces still reflects resistance to change. When external fields are applied, particles accelerate in ways that depend on their mass. This shows that inertia is not tied to classical motion alone, but is embedded in the most fundamental descriptions of matter. Feynman emphasized that this consistency is not guaranteed by theory alone. It is confirmed experimentally. Measurements of particle behavior repeatedly show that inertia behaves exactly as expected, even under extreme conditions. This reliability reinforces the idea that inertia is not an approximation, but a core feature of reality. At microscopic scales, inertia also explains why atoms and molecules have stability. If particles did not resist changes in motion, electrons could not maintain consistent behavior around nuclei, and atoms would not have well-defined structures. Inertia helps preserve order at the smallest levels, just as it does at larger ones. Feynman often pointed out that inertia at the atomic level is essential for temperature to have meaning. Temperature reflects the average motion of particles. Inertia ensures that this motion does not change erratically. When energy is added or removed, particles respond in predictable ways because their inertia governs how their motion can change. The microscopic view also reveals that inertia does not depend on complexity. Simple particles with no internal structure still exhibit inertia. This is a crucial insight. It shows that inertia is not the result of internal parts interacting or lagging behind. Even objects with no discernible internal mechanism resist acceleration. Feynman liked to challenge people who imagined inertia as a consequence of internal delays or hidden friction within matter. At the scale of elementary particles, such explanations collapse. There is nothing inside an electron to rub against. Yet inertia remains. This forces us to accept inertia as fundamental rather than emergent from simpler mechanical processes. At very high energies, inertia becomes intertwined with energy itself. As particles gain energy, their resistance to further acceleration increases. While the details go beyond classical descriptions, the central idea remains unchanged: matter resists changes in motion. Even when mass and energy blur into each other, inertia continues to regulate motion. Feynman often emphasized that this behavior places limits on what is physically possible. No matter how strong the force, particles cannot be accelerated arbitrarily without consequences. Inertia ensures that acceleration remains proportional to applied influence. This restraint is essential for the stability of physical laws. At the microscopic scale, inertia also underlies the conservation of momentum. When particles interact, their momenta change in ways that reflect their masses. These exchanges follow strict accounting rules. Inertia ensures that motion is redistributed consistently rather than created or destroyed. Feynman highlighted that these conservation laws are not imposed from outside. They arise naturally because inertia governs how particles respond to forces. Momentum conservation is not an independent principle layered on top of inertia. It is a consequence of it. Another important aspect is that inertia at the microscopic level is independent of environment. Whether particles are isolated in a vacuum or embedded in complex materials, their inertial properties remain the same. This universality allows scientists to predict behavior across vastly different systems using the same principles. Feynman also noted that inertia connects the microscopic and macroscopic worlds seamlessly. The inertia of a large object is simply the combined inertia of its constituent particles. There is no sudden transition where inertia appears. It accumulates. This continuity across scales is one of the reasons physics can bridge atoms and galaxies with the same concepts. The atomic perspective also reveals why inertia is so reliable. It is not an average effect that could fluctuate. It is present in every particle, at every moment. The collective behavior of matter inherits this reliability. Feynman emphasized that recognizing inertia at the microscopic level dissolves many misconceptions. It shows that inertia is not about size, heaviness, or visibility. It is about existence. If something exists as matter or energy with mass, it resists changes in motion. This realization deepens our appreciation of how simple rules give rise to complex behavior. The same inertial resistance that limits particle acceleration also enables the formation of stable atoms, molecules, and ultimately life. Without inertia at the microscopic level, complexity could not persist. At a philosophical level, inertia in the microscopic world reinforces the idea that nature values continuity. Even at the smallest scales, change is regulated. Motion evolves smoothly rather than erratically. Feynman often concluded such discussions by reminding listeners that looking deeper into matter does not remove mystery, it relocates it. We can describe inertia at every scale, but we still do not know why matter has this property. Yet the fact that it exists everywhere, from electrons to galaxies, is one of the most powerful unifying observations in physics. Through the atomic and microscopic view, inertia reveals itself not as a coarse macroscopic illusion, but as a precise universal rule. It is present wherever motion exists, quietly enforcing order and making the universe intelligible at every level. When considering why inertia matters for understanding the universe, Richard Feynman treated inertia not as a narrow topic in mechanics, but as one of the quiet pillars that make the universe intelligible at all. Inertia is not just about moving objects, it is about why the universe is predictable, stable, and capable of sustaining structure over time. Without inertia, the very idea of understanding nature through laws would collapse. Inertia matters because it establishes continuity. The universe does not reset itself at every moment. What exists now carries information from the past into the future. An object's current motion depends on its previous motion unless something intervenes. This continuity is not philosophical abstraction, it is a physical rule enforced everywhere. Inertia ensures that the present grows smoothly out of the past, allowing cause and effect to remain connected. This continuity is essential for prediction. Science depends on the assumption that if we know the present state of a system and the forces acting on it, we can predict what will happen next. Inertia makes this possible because objects resist changes in motion, small influences produce small effects, and large influences produce proportionally large effects. Without inertia, even the tiniest force could cause enormous unpredictable changes, making calculation and foresight meaningless. Feynman often emphasized that inertia is what allows the universe to be mathematically describable. Equations of motion work because inertia behaves consistently. If matter did not resist acceleration in a regular way, equations would fail to match reality. The success of physics, from classical mechanics to modern theories, rests on the fact that inertia is reliable. Inertia also matters because it removes the need for a preferred state of rest. There is no universal stillness against which all motion is measured. Constant motion and rest are physically equivalent states. This insight reshapes our understanding of space and motion. It tells us that the universe does not privilege one viewpoint over another. All inertial frames are equally valid. This equality is not just elegant, it is necessary for a coherent description of reality. Because inertia treats uniform motion as natural, the universe does not require constant input to maintain movement. Planets do not need engines to keep orbiting. Galaxies do not need continuous pushes to drift through space. Motion persists on its own. Forces are only needed to change motion, not to sustain it. This fact explains why cosmic structures can endure for billions of years. Inertia is also crucial for understanding stability. Stars, planets, atoms, and even everyday objects rely on inertia to avoid sudden collapse or explosion. Structures remain intact because their components resist abrupt changes in motion. Inertia dampens chaos. It ensures that disturbances propagate gradually rather than instantaneously destroying order. Feynman often highlighted that inertia makes conservation laws meaningful. Momentum is conserved because objects resist changes in motion. Energy calculations rely on this resistance being consistent. Without inertia, conservation would not hold in any useful sense. These conservation principles are not decorative features of physics, they are the backbone of explanation. Inertia underlies them all. On a cosmic scale, inertia explains why the universe can be studied historically. Light travels for billions of years carrying information from distant stars because it follows consistent inertial behavior. Galaxies move along predictable paths influenced by gravity, not random whims. Inertia allows the universe to have a history that can be reconstructed and understood. Inertia also matters because it connects the smallest and largest scales. The same principle that governs an electron's response to a force governs the motion of a planet. This unity allows physicists to apply similar reasoning across vast differences in scale. Without inertia as a universal rule, physics would fragment into unrelated domains. Feynman stressed that inertia protects the universe from absurdity. If matter did not resist acceleration, a tiny fluctuation could produce infinite motion. Reality would be violently unstable. Nothing could persist long enough to form atoms, let alone living beings. Inertia enforces moderation. It ensures that change happens in proportion to cause. From a human perspective, inertia shapes experience itself. Our sense of balance, motion, comfort, and safety all depend on it. Sudden changes feel dangerous because inertia resists them. Gradual changes feel natural because inertia can accommodate them. Our bodies have evolved in harmony with inertial laws, even if we do not consciously think about them. Inertia also gives meaning to force. A force is only identifiable because it produces acceleration against inertia. Without inertia, the concept of force would dissolve. There would be no way to distinguish between influence and coincidence. Inertia turns interaction into measurable effect. Feynman often pointed out that inertia is one of those ideas that becomes more profound the more deeply it is considered. At first, it seems obvious. Objects keep moving. But upon reflection, this behavior is astonishing. Why should matter care about its previous motion? Why should the universe enforce continuity so strictly? Physics can describe inertia, but it cannot explain why it exists. That mystery is not a failure, it is a reminder of how deep the question goes. Inertia also matters because it allows complexity to arise. Complex systems require stability over time. Chemical reactions, biological processes, and technological systems all depend on controlled motion and predictable response. Inertia provides the physical patience needed for complexity to develop and persist. Feynman emphasized that understanding inertia changes how we view motion itself. Motion is not something that needs constant explanation. Change is what needs explanation. This reversal is one of the most important conceptual shifts in science. It moves us away from thinking of nature as constantly active and towards seeing it as conservatively evolving unless disturbed. At the deepest level, inertia matters because it makes the universe intelligible rather than magical. Events do not happen just because. Motion does not change without cause. This insistence on reason is built into the fabric of reality. Inertia enforces it everywhere. In the end, inertia is not just a rule about objects. It is a statement about how the universe values continuity, proportionality, and order. It allows the past to influence the future, causes to lead to effects, and laws to describe behavior across time and space. Feynman's way of explaining inertia leaves us with a quiet but powerful conclusion. The universe is understandable because it resists change. That resistance is not an obstacle to knowledge, it is the foundation of it.